Welcome to our quantum deep dive.
Great to be diving in.
Today we're tackling something really fundamental, maybe even a bit mind-bending, the Heisenberg uncertainty principle. You might also know it as the unsure-for relation. And we're doing this exploration based entirely on a really insightful essay provided by you, the listener, which was written by Jorg O. Schneeppet.
Yeah, it's a great starting point.
So our mission basically is to unpack what this principle actually is, why it's so important in the quantum world, and, well, where we see its effects pop up. Ready to jump in.
Let's do it. Okay, so the uncertainty principle, at its core, it's not about like shaky hands or bad measuring devices.
Right, not just experimental error.
Exactly. It's a fundamental limit baked into nature itself on how precisely we can know certain pairs of properties for a quantum object, think like an electron, at the very same instant.
And the classic example, the one everyone hears about, is position and momentum.
That's the one. Position, where the particle is, let's call this uncertainty delta x, and momentum delta p, which is basically its mass times velocity, how it's moving.
And Werner Heisenberg, he was the one who formalized this.
He was. Back in 1927, he gave us the mathematical framework.
Which involves that famous inequality, right?
Spot on. It's delta x and delta p aren't just errors. They're uncertainties, standard deviations.
Yeah, think of them as the inherent spread or fuzziness in the possible values you might measure for position and momentum. A standard deviation gives you a measure of that spread.
And the he-bar.
That's the reduced Planck constant. It's a fundamental constant of nature, super tiny, but it defines the scale where quantum effects like this become really important.
So the equation says the product of those two uncertainties, it can't be zero. It has a minimum value.
Precisely. That product, delta x times delta p, has to be greater than or equal to a bar 2. It cannot be smaller.
And that immediately implies a trade-off. Absolutely. If you design an experiment to measure position really precisely, so delta x becomes very small,
then delta p has to get bigger to keep the product above that ℏ2 limit.
Exactly. Your knowledge of momentum becomes fuzzier. And the other way around, know the momentum precisely, and the position gets uncertain. You just can't have both perfectly sharp for the same particle at the same time.
Okay, that feels weird compared to, say, tracking a baseball. I can know where it is and how fast it's going pretty well. What's different down at the quantum level?
It all ties back to something even more fundamental. Wave-particle duality. Quantum things aren't just particles, and they aren't just waves. They're both, somehow.
Ah, the famous double-slit experiment comes to mind.
Perfect example. You shoot electrons, one by one, at two slits. If you just let them hit a screen behind, they build up an interference pattern, like waves overlapping.
Even though you sent them one at a time.
Right. But, crucially, if you put detectors at the slits to see which slit each electron goes through,
you find out its position more precisely.
And poof. The interference pattern vanishes. They just land in two clumps behind the slits, like particles. The act of measuring the position forces it to choose a path and lose its wave-like spread.
Knowing the which path information kills the wave behavior.
In essence, yeah. And that wave nature is tied to momentum through the de Broglie relation, lambda HEP. Wavelength and momentum are linked.
And these things we measure position, momentum, energy, time in quantum mechanics. We call them observables.
That's the term. They're the quantities we can, in principle, measure. And importantly, in QM, they're represented by mathematical operators. Measurements don't just reveal pre-existing values. They often involve probabilities and can change the state itself.
Okay, back to the math for a sec. We had delta x cc dot, delta p gec frac bar. You said it applies to pairs of properties. Is there a more general rule?
There is. It gets a bit more abstract, but for any two observables, say A and B, their uncertainties are linked by delta. Delta B, gec frac 1, 2, left wrangle A, B wrangle right.
Whoa, okay. What's the AB part?
That's called the commutator. It basically measures whether the order of applying the operators A and B matters. If A, B is 0, they commute, and there's no fundamental uncertainty limit between them. But if it's not 0,
then they don't commute, and you get an uncertainty relation.
Exactly. And for position x and momentum p, their commutator x, p is a jack bar, which is definitely not 0.
So the math itself shows they're incompatible in this way.
Precisely. The non-zero commutator is the mathematical root of the uncertainty principle for that pair. It proves they can't simultaneously have perfectly defined values.
Okay. Besides position and momentum, is there another really key pair?
Yes, the energy-time uncertainty relation. Delta T white, this one relates the uncertainty in the energy of a system, delta E, to the uncertainty in the time interval, delta t, over which something happens.
And that's important for what kind of things?
Oh, loads. Particle decay times, quantum tunneling electrons sneaking through barriers they shouldn't have the energy to cross, and as the essay points out, these really weird quantum fluctuations in empty space.
It still feels a bit like maybe if we just built better microscopes or better clocks. Why are we so sure this isn't just a technological limit we'll overcome?
That's such a crucial point to grasp. It is absolutely not a technological limit. It's fundamental. It comes from the wave nature itself.
How so?
Think about describing a particle with a wave function. If you want that wave function to be very narrow, very localized in space, meaning delta x is small.
You know its position well.
Right. To build that sharp peak, mathematically, you have to add together lots of waves with different wavelengths. It's like building a sharp musical note from many different frequencies.
And different wavelengths mean different momenta because of de Broglie.
Exactly. So a state that's narrow in position must be made of a wide spread of momenta. Delta p is large. And conversely, a state with a very precise momentum, like a pure sine wave, has only one wavelength, which means it's spread out all over space. Delta x is large.
Ah, so the very mathematical tools we use to describe waves force this relationship.
Yes. They're what mathematicians call Fourier partners. The shape of the wave in position space and the shape of its corresponding wave in momentum space are linked by this transform. You can't make both arbitrarily narrow simultaneously. The maths, like the Cauchy-Schwarz inequality mentioned in the essay, proves it.
In Heisenberg's microscope thought experiment, how does that fit?
It's a great illustration, not a proof, but an illustration of the disturbance involved. Imagine trying to see an electron with a supermicroscope. To get good resolution, pinpoint its position, delta x small, you need light with a very short wavelength.
High-frequency light.
Which means high-energy, high-momentum photons. When one of those photons hits the electron so you can see it.
It gives the electron a big kick.
A big, unpredictable kick. So the very act of measuring position accurately, delta x small, introduces a large uncertainty in its momentum, delta p large.
So trying to measure one messes up the other because of the interaction needed.
Precisely. It shows it's not just about passive observation. Interaction is required. And that interaction, governed by quantum rules and wave properties, causes an unavoidable trade-off. It's not just clumsy measuring.
Okay, so let's really try to nail this down. It is not measurement error. It is not technological limits.
Correct, on both counts. It is a fundamental property of quantum systems. In classical physics, we assume a particle has a definite position and momentum, even if we haven't measured it yet. In quantum mechanics, according to the standard view, a particle simply does not possess simultaneously definite values for both position and momentum beyond the limit set by Lake-Bartu. No such state exists.
Wow. So the property isn't even there to be measured perfectly.
That's the implication.
Yeah.
The state itself contains this inherent fuzziness. The mathematical framework proves it's unavoidable, and phenomena like vacuum fluctuations, which we can touch on, seem to be real-world consequences.
Now, how is this different from the observer effect? People often mix those up.
Good distinction. The uncertainty principle is about the inherent limits on the precision of certain pairs of properties within a quantum state. It's about the fuzziness that exists whether you measure or not.
Okay.
The observer effect is the separate, though related fact that the act of measurement itself generally disturbs the quantum system, like making a measurement on a superposition forces it to collapse into a definite outcome.
So uncertainty is about the state's inherent limits. Observer effect is about measurement changing the state.
Exactly. Measurement reveals information subject to the uncertainty limits and also causes the state change described by the observer effect. They're linked but distinct concepts.
Okay, so if this uncertainty is so fundamental, it must really shape how quantum mechanics describes things.
Oh, absolutely. It dictates the nature of quantum states. Because of uncertainty, you can't write down a wave function where both position and momentum are perfectly sharp. Mathematically, a state cannot be an eigenstate, a state with a definite value for both the position operator and momentum operator simultaneously.
What?
Because, as we said, those operators don't commute. XP isn't zero.
So the classical picture of a tiny dot with a precise location and speed just dissolves at this level.
It really does. We often use wave packets instead. A wave packet is like a compromise. It's a superposition of waves with slightly different momenta constructed so it's somewhat localized in space and somewhat localized in momentum.
It has some spread in both delta x and delta p.
Exactly. It visually represents that trade-off.
Yeah.
There's a specific type, the Gaussian wave packet, that's famous because it's the most classical state you can have. It actually minimizes the uncertainty product hitting that x bar 2 lower bound.
Let's circle back to the energy-time uncertainty, delta E frac bar 2. Where does that pop up in ways that are maybe unexpected?
This one is huge in quantum field theory, or QFT. QFT describes fundamental forces in particles in terms of fields filling space.
Yeah.
Particles are like excitations in these fields, and the energy-time uncertainty allows for a kind of loophole in energy conservation. Energy doesn't have to be perfectly conserved, provided the violation only lasts for a very short time, delta T, limited by the uncertainty delta E.
Like borrowing energy from the universe, but you have to pay it back super quickly?
That's a great analogy. And this borrowing allows for the existence of virtual particles. They pop into existence out of the vacuum, mediate forces like virtual photons carrying the electromagnetic force, and then disappear again, all within the time limit allowed by delta E AU dot delta T.
They're not real particles we can catch.
Not in the same way. They exist only fleetingly as intermediate steps in interactions. But their effects are very real.
And this implies the vacuum, empty space, isn't really empty.
That's one of the wildest consequences, vacuum fluctuations. Because of energy-time uncertainty, the vacuum is seething with these virtual antiparticle pairs constantly popping in and out of existence. It's a dynamic, fluctuating state.
And we can actually see effects of this. It's not just theory.
Oh, yes. The Casimir effect is a prime example. Put two neutral metal plates very close together in a vacuum. They attract each other.
Why?
Because the tiny gap between the plates restricts the kinds of virtual particles that can pop into existence there, compared to the unlimited space outside. This creates a tiny pressure difference, pushing the plates together.
Wow.
And there are other effects too, like the Lamb shift, tiny shifts in atomic energy levels caused by interactions with these vacuum fluctuations, and even links to things like Hawking radiation from black holes.
So this fundamental uncertainty literally sculpts the vacuum and mediates forces.
It's woven into the very fabric of how particles interact and how reality behaves at its most fundamental level.
Now, thinking about technology, this seemingly fuzzy aspect of nature must be critical for quantum technologies.
Absolutely foundational, especially in quantum cryptography. The whole idea of secure quantum communication relies on the fact that measuring a quantum state disturbs it, which is a direct consequence of uncertainty.
How does that make it secure?
Well, if an eavesdropper, let's call her Eve, tries to intercept and measure the quantum bits, say, photons being sent between Alice and Bob.
She has to interact with them.
Right. And her measurement, because of the uncertainty principle, especially if she guesses the wrong measurement basis, will inevitably change the state of some of those photons. When Alice and Bob later compare notes about a subset of their data, they'll find discrepancies that wouldn't be there otherwise.
So Eve leaves footprints.
Exactly. The act of observing introduces detectable errors. The famous BB84 protocol works precisely on this principle. Alice encodes bits using different bases, like polarization directions. Bob measures randomly. If Eve intercepts, she has to guess a basis, introducing errors if her guess is wrong relative to Bob's measurement on that photon, revealing her presence when Alice and Bob compare notes.
That's clever, turning a limitation into a feature. What about quantum computers?
Uncertainty is key there, too. Qubits operate using superposition and entanglement. You can't simultaneously know a qubit's value perfectly in multiple complementary bases, say, its value in the standard O1 basis and its value in a diagonal plus basis. Trying to measure one fuzzes out the other.
Then that's useful.
It's part of what gives quantum computers their power. They manipulate these delicate, uncertain states where information is encoded in probabilities and correlations that classical bits just can't represent. Quantum algorithms leverage this fuzziness and superposition.
But isn't quantum noise and decoherence a massive headache for building these things? Is that related?
Very much so. Qubits are incredibly sensitive to their environment. Any unwanted interaction can cause their delicate quantum state, their superposition or entanglement, to collapse. That's decoherence. This sensitivity is intrinsically linked to uncertainty. The system is easily perturbed because its properties aren't rigidly fixed.
So controlling them is hard.
Extremely hard. That's why researchers work so hard on error correction codes and keeping qubits super isolated. But interestingly, sometimes that quantum noise, rooted in uncertainty, can be harnessed, for instance, to generate truly random numbers.
Okay, and the measurement process itself in a quantum computer?
It's called projection measurement. When you measure a qubit in superposition, it collapses projects onto one of the definite basis states, like 0 or 1, with a certain probability. Because of uncertainty, one measurement doesn't tell you everything. especially if the state was prepared or needs to be known in multiple bases. That's why fully characterizing an unknown quantum state tomography requires measuring many identical copies in different bases and statistically reconstructing the state.
Uncertainty seems like it's everywhere in the quantum tech world. Has it been tested rigorously over the years? What's the proof?
Oh, absolutely. It's one of the most thoroughly tested principles in physics. Decades of experiments confirm it with incredible precision.
What were some of the early confirmation?
Well, even experiments predating the formal principle hinted at it. The Stern-Gerlach experiment showed measuring electron spin in one direction randomizes it in others. Spin components also have non-commuting operators. And the double-slit experiment is a beautiful demonstration of the core idea. Gain which path information, delta X smaller, lose interference, delta P spread needed for waves gets lost. Heisenberg's microscope was the thought experiment connecting these.
And more recently?
Modern experiments are amazing. Quantum optics lets us play with single photons, directly measuring the trade-offs in position, momentum, or energy time. Atom interferometry uses clouds of ultra-cold atoms, which behave like matter waves, to test uncertainty on almost macroscopic scales. And things like quantum dots, tiny semiconductor crystals trapping single electrons, let us probe uncertainty at the nanoscale.
Are they just checking Heisenberg's original formula or looking for more?
Both. The standard inequality, delta X, delta P, Gebra, bar 2, holds up incredibly well. But scientists are always pushing. Are there situations where slightly different uncertainty relations apply? Can we find loopholes? Techniques like weak measurement try to gain some information with minimal disturbance, giving different perspectives. And experiments testing Bell's inequality, while mainly about entanglement, strongly rule out simple hidden variable theories that would try to explain away quantum uncertainty as just ignorance.
So what's the next frontier for testing it?
People are looking at using uncertainty-limited measurements for ultra-precise quantum sensors detecting tiny gravitational waves, perhaps. Building fault-tolerant quantum computers inherently tests our ability to control states governed by uncertainty. And then there's the big theoretical frontier. How does uncertainty work when you combine quantum mechanics with gravity? What happens near a black hole singularity or the Planck scale? That's where things get really speculative but exciting.
This definitely steps into deep philosophical waters, doesn't it? The meaning of it all.
It really does. The uncertainty principle is central to the Copenhagen interpretation, the sort of standard way of thinking about quantum mechanics developed by Bohr, Heisenberg, and others.
And what does that interpretation say?
It basically says that quantum systems don't have definite properties like position and momentum before you measure them. They exist in a superposition of possibilities described by the wave function. Measurement forces a collapse into one specific outcome. Uncertainty, in this view, means that properties like position and momentum aren't just sitting there waiting to be revealed. They are, in a sense, defined by the measurement act, within the limits allowed. Probability is fundamental.
That's a radical departure from classical thinking. Was everyone on board?
Oh, definitely not. Einstein famously hated it. He felt quantum mechanics was incomplete. His line, "God does not play dice," summed up his belief that there must be some underlying deterministic reality, hidden variables, that would remove the randomness and uncertainty if only we knew them.
But experiments seem to go against that. The EPR paradox and Bell tests.
Exactly. The EPR paper tried to argue quantum mechanics was incomplete using entangled particles. But John Bell later showed that if reality is based on local hidden variables, Einstein's assumption, then correlations between entangled particles must obey a certain inequality. Experiments, starting with the Lane aspect and many others since, have shown Bell's inequality is violated, just as quantum mechanics predicts.
Meaning no local, classical hidden variables can explain quantum mechanics.
That's the standard conclusion. It strongly supports the idea that the uncertainty and weirdness are genuinely quantum, not just missing information.
Are there other ways to interpret uncertainty, though?
Yes, alternatives exist. Bohmian mechanics proposes particles do have definite positions, guided by a pilot wave. Uncertainty here arises from our ignorance of the precise state of this wave. The many worlds interpretation suggests measurements cause the universe to split, with all possible outcomes happening in parallel universes. Uncertainty, then, is about which branch we find ourselves on. These offer different philosophical pictures, but they still have to account for the mathematical structure and experimental results of uncertainty.
It really does challenge our fundamental picture of reality and information.
Absolutely. It suggests knowledge is fundamentally tied to interaction. It challenges classical determinism. You can't know the initial state perfectly to predict the future path. And it's related to things like the no-cloning theorem.
Yeah.
You can't perfectly copy an unknown quantum state, partly because measuring it to read it inevitably disturbs it due to uncertainty.
That is definitely a lot to wrap your head around.
It's a deep principle with far-reaching consequences.
Okay, let's try to pull together the main threads from this deep dive, drawing on Yorgo Schneppat's essay.
Right, so the big takeaway. Heisenberg's uncertainty principle, that delta x EC dot delta P Gek-Bartu relation, isn't about faulty gear. It's fundamental, unavoidable.
Baked into the wave nature of quantum stuff.
Exactly.
Yeah.
And its effects whipple through everything quantum. It shapes how we even describe states. It leads to things like virtual particles and vacuum energy in QFT.
And it's the engine behind quantum technologies like crypto and computing, both enabling them and presenting challenges.
Right. And it stood up to rigorous experimental tests for nearly a century.
And philosophically, it just turns our classical picture of reality on its head.
It forces us to confront probability, measurement, and the limits of knowledge in a totally new way, sparking ongoing debate.
What are the big questions still lingering around it?
Well, is the standard inequality the absolute final word?
Yeah.
How exactly does it mesh with gravity at extreme scales? What are the ultimate practical limits it imposes on technology we want to build?
And researchers are actively poking at these questions.
Constantly. Pushing sensor precision, building better qubits, theorizing about quantum gravity uncertainty is relevant to all of it.
Amazing how a principle from the 1920s remains so central.
It really is. It's not just a limitation. It's a defining characteristic of how the universe works at its deepest level, probabilistic, interactive, and fundamentally uncertain.
Which brings us to maybe a final thought, inspired by Yorgo Schneppat's essay for you to mull over. If a quantum particle doesn't have a precise position and momentum simultaneously before we look, what does that imply about reality itself when we're not looking? Is the fundamental nature of existence more like a set of potentials waiting to become definite through interaction?
Something deep to think about, definitely.
Thank you for joining us on this Quantum Deep Dive.